How do artificial neurons and language models create categories of thought to understand and analyze their environment as it appears to them? What are the characteristics of this conceptual segmentation at the neuronal level? How do the mathematical operations performed by formal neurons shape the way artificial intelligence organizes its internal world of information about its environment? Exploring these questions requires understanding that the cognitive and conceptual properties of artificial neural networks do not emerge by magic or chance. On the contrary, in a dynamic of embodied cognition, these properties result directly from the specific material characteristics and mathematical and architectural constraints of the AI system within which they emerge. A key element in the operation of neural networks is the aggregation function, which linearly combines the inputs, categories of thought, of each neuron to produce its output, a new, more abstract, refined category of thought for the type of task to be performed. This mathematical function thus plays a crucial role in creating the categories that each artificial neuron uses to process the information presented to it. To investigate this topic, we studied the statistical characteristics of the 100 most frequently recognized words, or tokens, segments of words, by the 12,800 neurons of the first two perceptron layers of OpenAI's GPT-2 XL language model. This represents 1,280,000 word occurrences analyzed. An artificial neuron reacts to a word with a certain intensity. This intensity shows how much the neuron recognizes or identifies the word, indicating to what degree this word belongs to the category the neuron detects. This principle guided the methodology we employed. We identified a first mathematical cognitive factor, driven by the aggregation function, explaining how a neuron constructs the category of thought it is designed to detect in the words it analyzes: synthetic categorical priming, or the X effect. This effect refers to the fact that the more a word activates a neuron in a neural layer N, the more this word will activate the neurons strongly connected to this precursor neuron in the next layer N+1 via an activation propagation mechanism. In other words, the category of thought created by a target neuron in layer N+1 is preferentially composed of the words that strongly activated its precursor neurons in layer N. For example, the more general and abstract thought category habitat of a target neuron in layer N+1 will form because the words house, shelter, cabin, and villa have strongly activated its precursor neurons in layer N. We identified a second mathematical cognitive factor that helps explain how a neuron constructs its associated thought category: synthetic categorical attention, or the W effect. This phenomenon of synthetic cognition manifests in the way that the thought category of a target neuron, layer N+1, is formed by deciding to focus its interest on certain and only certain categories of thought from its precursor neurons, layer N. The newly constructed thought category thus results from different selected categories combined within this new category. This results in a categorical complementation mechanism. The category emotion of a target neuron, layer N+1, will, for example, be formed by extracting and juxtaposing from the categories of precursor neurons, layer N, one group of words related to liking, love, adore, and another group related to disliking, hate, despise, detest. Similarly, the category auditory of a target neuron will be generated by extracting and combining from its precursor categories a set of word segments, listen, hear, perceive, related to hearing, and another class of words, sound, noise, melody, related to the concept of hard elements. Finally, we have identified a third explanatory component of the process behind the genesis of synthetic thought categories, triggered by the aggregation function of artificial neurons, synthetic categorical phasing, or the sigma effect. This mechanism refers to the fact that when different categories, potentially conceptually distinct, are jointly activated in precursor neurons for a given word, these categories enter into a categorical echo, highlighting this word in the newly formed category within an associated target neuron. This manifests through a process of categorical intersection. For example, a precursor category, layer N, includes in its extension the words knife, gun, mortar, bomb, axe, cleaver, and sword, lexical field of weapons, while another category, also in layer N, consists of cleaver, spatula, strainer, knife, blender, and mortar, lexical field of kitchen utensils. At the intersection of these two distinct lexical fields, we find the words knife, mortar, and cleaver. These specific words simultaneously activate the two involved precursor neurons in layer N, resulting in the strong activation of their associated target neuron in layer N+1. The category represented by this target neuron will therefore be specifically linked to the particular words knife, mortar, and cleaver. Through this process, a new, more refined category is formed, denoting specific tools that have the dual characteristic of being both kitchen utensils and weapons. Let's consider another example. A precursor category related to management includes words such as executive, manager, leader, chief, director, CEO, and supervisor. Another category pertaining to top management in the private or public administration sector includes words such as director, executive, CEO, minister, and senator. The three words director, executive, and CEO, which are common to both categories, become strongly activated within the associated target neuron, thereby leading to the formation of a new abstract category that synthesizes the previous two, the category of private top management. These three mathematical cognitive factors of categorical abstraction performed by artificial neurons work in concert. They reinforce each other, and when they are simultaneously significant for a group of words belonging to a precursor category in layer N, they will cause the extraction from this precursor category and at the level of a target neuron in layer N+1 of a categorical subdimension. This categorical subdimension will constitute part of the semantics of the new category carried by this target neuron, which will be complemented by other categorical subdimensions. In the examples mentioned here for didactic purposes, we used cases of simple-to-understand categories analogous to existing human thought categories. However, this extraction of categorical subdimensions is not a passive reading of pre-given and pre-existing properties in a world of objects and properties that merely need to be selected. On the contrary, it is an abstraction that fabricates entirely new, unique, and complex thought categories, resulting from the original and subtle combination of preliminary thought categories. In other words, this abstraction is not a simple abstraction in the sense of Piaget or empiricist philosophy. These new thought categories do not necessarily correspond to existing categories in human culture, as comparative anthropology, intercultural psychology, animal psychology, and the history of science continuously demonstrate. These innovative thought categories can thus be polysemous in relation to human thought by combining entities, for example, notions of food, vision, and electronics, that human cognition is not accustomed to coordinating within a single unified concept. These thought categories may correspond to purely mathematical constructs associated with statistically repeated co-occurrences of phenomena that would appear semantically disparate to us. As a result, these original categories would seem like alien concepts, completely disconnected from any tangible observations that we, as human beings, could experience. This conceptual singularity of thought categories generated by the artificial intelligence of language models stems from the fact that, during its training phase, a neural network essentially seeks only one thing: to parameterize the values of the different elements of the aggregation function of each of its constituent neurons. This is done to generate an original system for categorizing the world of human texts, a segmentation that ultimately proves functional in relation to human expectations, integrated through feedback directly or indirectly provided to the AI during its deep learning phase. This categorical segmentation thus aims to generate a structural coupling, in Varela's sense, between the internal world of a neural network and the external world of human data to which it is exposed. This coupling manifests through the emergence of regularities in the external world, that of text and data. In other words, it involves assigning internally constructed meanings to this undefined external world, meanings that are entirely specific to the architectural and mathematical structure of each particular artificial intelligence system. These internal meanings enable effective interaction, at any cost, with this external universe, which remains unbounded and exists beyond the informational closure of the AI system. Moreover, this structural coupling gives rise to novel meanings, original synthetic thought categories, that are statistically functional for this purpose. This emergence occurs over time through the experience of interaction with the world of words during the neural network's training phase. Thank you for joining us on this exploration of synthetic thought in artificial intelligence. You can find the article mentioned in the video, as well as all the work from Neocognition Lab on neocognition.org. See you soon for a new video.